Ricky Martin was a national treasure. Let the record show. Red Aspintope, did you hear the new Taylor Swift?
I haven't either.
I heard it's a bop. It slapped, right, Lillian?
You know, her albums are bops like every 2 albums. They're okay.
Like If You Cry every time.
My favorite Taylor Swift song is "Look What You Made Me Do." Look what you
How did I lose? I lost. Oh, here it is. Okay, it's under the. Okay, so did you guys? What's the question? That we're confused about.
What am I doing?
Setting up the constraint and then like setting up the maximize or minimize.
Okay, is there one that we've already done that you're still stuck on, or?
Like 4. I feel pretty good about 3.
Sure, 4. Hannah disagrees. So, okay, the constraint is often stated as a fact, meaning the perimeter of a rectangle is 40 feet. So when you read that little sentence, that's your constraint. So here's a rectangle, and a rectangle has width and a length. And so when it says the perimeter is 40, that's your constraint. So the constraint would be that 2 times L plus 2 times W is 40. So that's a constraint, right?
Yep.
We could, of course, rewrite that constraint as L plus W equals 20. That's an equivalent constraint. That's a lot easier to work with. So does that answer that question?
Yep.
Okay, so the constraint is something you're constrained to have. So that must be the case. Then it'll say, usually the word find is in there, or calculate, or optimize, or minimize, or maximize. It'll say, in this case, it's find the dimensions that maximize the area. So then you go, okay, what's the quantity? So the quantity is area. So you say area first, and then what you do is you write a formula for what the quantity is you're trying to optimize. So in this case, it's L times W. So this is the optimization thingy. The thing you're trying to optimize is the area. Does that answer that part?
Yep.
No. Any further questions on setting up the constraint or do that?
Well, I guess then you just sub it in, right?
Yeah. And then we've done sort of this is the big thinky winkies really, is setting it up. The farther you go in math, the more it becomes setting up the problem is like 99% of the brain work, and then the arithmetic is like kind of an afterthought. But especially differential equations. So anyway, so you have this. Now you go, okay, let's do a substitution. Because right now you'd have to visualize this as like a 3-dimensional space, meaning you have 2 different variables so you're trying to take this and transform it into. You want to transform it into how does the area depend on a single variable? So let's make the single variable, I don't know, W. So if I solve this, so let's do that. Let's solve this. L is equal to 20 minus W, right? And then sub that in for that L. So the big step here is a substitution. Heads up, Aspen. Oh, so close. Okay. So anyway, let's do the substitution. So the area is 20 minus W multiplied by W. What shape is that? It's a sad parabola.
Oh, it is. It is. Yeah.
Right, Lillian? It's a parabola that has just listened to the new Taylor Swift album. Okay? I thought her albums were happy. Is this new one it's all full of sad songs?
I want to hear it.
I haven't heard it yet. I listened to it today. Huh?
Why can't you listen to it and tell me?
I will. So if you graph this, here's where you can kind of see the answer just graphically. This is a parabola. I could rewrite it like this. So So 20 times W minus W squared. Although that's the more useful way to express it to graph it, because you know that it crosses at 0 and 20. Cool beans? We know that parabolas have symmetry, so you kind of already know where this peak's going to happen. The peak's going to happen at 10. Let's say we weren't sure about that. It's not, okay, that's fine. Take the derivative. You get 20 minus 2W. And then, so what is this point? What's happening at this point? Well, the derivative is 0 there at the peak. So I set my derivative equal to 0, and I solve, I get 10. And of course, if I go back to my original constraint, if W is 10, then L has to be 10 as well. Which gets us the famous elementary result from geometry, which is, well, what shape would maximize my area given, say, a finite amount of fence? It's a square. So, yay!
I guess the other question I just thought of was, what is the true final answer? Is it the graph or is it the 10-10?
Well, let's see, the question, just it depends on how the question's worded. It says, find the dimensions so that the rectangle has a maximum area. So the way that's phrased, this is the final answer here. The dimensions are a 10 by 10 rectangle would have, a 10 by 10 rectangle obeys the constraint, the perimeter is 40, and it maximizes the area by having an area of 100. You can test a different one out if you want. You can test out, I don't know, suppose you would have an area of, or a perimeter of 40, it could have been maybe 12 and 8. Well, 12 times 8 is 96, so a little bit smaller area than we got with 10 by 10. Yes, cool beans? Yes. Further questions? Are there more? Yes, Aiden.
Why did you set it equal to 0 instead of, never mind. Never mind.
That's a good question, though. We're setting the derivative equal to 0 because we know that this is a nicely behaved function, and nicely behaved functions hit their peaks or their valleys at spots when the derivative is 0. Let's do, why don't you guys try to set up 15? I'm going to go obtain a new marker, or maybe a couple markers.
It's a box.
They're green and red.
It's Christmas time.
No. And black.
Well, I said I didn't sleep, but I never sleep.
One of my stupid things last night where I went to bed at 8.
Did you step on my
4 and couldn't go to bed. So I have very long sleep.
Oh, yeah, that is a nice one.
Man, what's this?
Oh, now.
I fell asleep at maybe 2, 3. I don't know. Something. 4. Sometime.
I think the time.
But I don't know. A box with no lid.
A box with a lid. I don't know how to do boxes.
Well, it's lengthened with fence height.
Right.
I just put the slime mold on my paper.
Yeah, you just put some slime mold on there. You'll be good. You'll be all set. So, although Aaron, you mentioned the slime mold, but what's interesting on a problem like this, a lot of times you can look, say, for like a cultural answer, whereas, I mean, this is just kind of a boring one, a box, but suppose that people have been constructing boxes for a long time, which they have. A lot of times you can, the optimum solution will just emerge sort of naturally without any calculation. You'll say, oh, people have been doing this for a long time, and you'll say the process that they've discovered turns out to be mathematically optimal. Another example of emergent phenomenon.
The evolution of boxes.
I'm trying to think of like maybe a more interesting example.
I mean, like cars and like the construction of those. Well, I guess that isn't like
I'm sure you can find like a society that has no technology really, and they say they perform some process to whatever, get water or something, and you can show, oh wow, no one ever sat down and like analyzed it, but their process is extremely efficient. Oh, I just thought of an example. Mr. Doggy does calculus. Okay, so we'll do a problem like this actually. So Mr. Doggy, this is water. This is the beach. Here's Mr. Doggy.
Oh, God.
Okay. You throw your bone.
Oh, boy.
You throw your bone into the water, or a stick, or whatever, it's frisbee.
Oh.
You say, go get the bone.
Most efficient.
What does Mr. Doggy do? Well, if he wanted to minimize his time spent in the water, he would obviously have to go to this point, right?
That's not allowed.
If he wanted to go shortest distance overall, he would go directly to the bone. But Mr. Doggy performs the calculus in his head. He says, wait a second. Moving in the water is more energy costly than moving on the beach. So what I'm going to do is I'm actually going to find a balance point where, yes, this is the shortest distance, and this minimizes the amount of time in the water. But to minimize my overall energy used, I will find some other point in the middle. And you can show that they actually tend to do this kind of thing. And actually, light does the same thing. If you have, say, here's some oil, and you have a laser, and you shine the laser into the, it'll actually bend.
Yep.
And what the light does, the light is actually minimizing the say the light, quote unquote, wants to get from the laser pointer to whatever, some target. This actually minimizes the amount of time the light takes to get there. How does it know? How does Mr. Lightbeam know, Aspen Taupe? Tell me that.
My dog is going to a spaz to do that.
Or I've seen a dog do this, where like there was a staircase. This happened to me. This is like a room. And I was here. And then there were stairs. And then the dog was here. He says, hello, I want to be with you. And he knows that the minimum distance is just to jump down the stairs.
Into your arms.
Right. He knows that this would also be a path. Go to the bottom of the stairs. But he would always go like, he'd calculate, well, the minimum energy would probably be like go down a couple stairs up, then jump down the stairs. He'd find this optimal solution. So if you look at the oil rig problem, the oil rig problem is actually very similar to that. Anyway, where were we? Box.
I'm always like,
Box.
probably it's just like,
Thanks.
sure you know.
I mean, geez, have you ever thought about how much goes into just like walking or catching a ball? It's crazy. You know how difficult it is to program a robot to walk? There's the number of calculations your brain is performing, and not only your brain, your whole body is this big machine that to get you to walk is just an insane triumph of like calculation. I don't know how to call it calculation. Just have wheels. There you go.
Just start rolling.
Okay, so Mr. Box.
Well, Paul, they call
Down to the beach.
Oh, what?
Never mind.
It was very bad.
Okay. So a box, it says it has a square base. So let's call the base x by x, because that's what the squares have the same length and width. And then it says, well, the box has to have a height of some kind, right? And the problem does not say that the height is like anything different, right? Then, or I guess, if it said the height is the same as the base length, that would just turn this into like, basically like a basic geometry question. So, okay, calculate z equal to that area, you get the answer. So what makes it a calculus question is, these are two different values perhaps, but we know that the constraint is that, so constraint, who wants to tell us what the constraint is? Anyone? Not even I should have been more specific. Not the formula, just generally it's about volume or surface area. Surface area. The constraint is that the surface area is 48. Does that make sense?
Yeah.
So if you got the formula, that's awesome. The formula for surface area would be, there's 4 of these faces, and these faces are x by h. So I'd say x times h times, there's 4 of them, and I'm missing one thing. Don't forget the bottom of the box. The bottom of the box has
X squared.
x squared. Cool beans? So that's the constraint. All right, before we move on, I don't want to go too fast. Does anyone have any questions on why that's the constraint? So the 4 vertical walls plus the bottom of the box must be combined to be 48 square inches of material. So that's an area statement. Again, there's no lid. So that's why there's only 1x squared. If there was a lid, you'd say there'd be 2x squared.
So now like the minimize, maximize, you're getting the volume.
Well, now, yes, exactly. So the thing we're trying to optimize, we are trying to maximize the volume. So when you want to maximize the volume, you're going to write a formula for the volume. So what's volume formula? Well, volume of a box would be, or the area of the base multiplied by the height of the box. So that's the volume, x squared times h. Okay, so, tricky. What do?
Solve for H.
Yes. This guy is going to be very difficult to solve for x. You could theoretically solve for x, but that makes things way harder. So let's solve this for h. H is 48 minus x squared divided by 4x. That make sense?
Yeah.
No questions? Now, we can substitute that in for the h. Squared times looks scary,
Yeah.
but it's actually not that bad because this x is going to cancel out one of those x's, and we're actually just going to have a polynomial. That's nice. Yay! Yay! Okay, so I'll show both steps here because does that make sense? How this x times x, one of those x's will cancel that x,
Yeah.
and so what I'll have left over is x out here times, or actually, you know what might be a nicer way to write it would be to think of this x squared over 4x as just being x over 4. I don't know, stop me if that's confusing. So I just thought of this as like, it's kind of like if you had, say I had 3 times, or a better example is, say I had 12 times 5 over 3. I might rethink that as, I really have the same as 12 over 3 times 5. That's basically what I did there. The plan, the nefarious plan of distributing this. I'm guessing, I don't know, maybe some of you guys were like, well, I arrived at this a quicker way. If you did, that's great. You can congratulate yourself. That's on a job well done. Oops, it's this, not the computer. So, anyway, if you arrived at that
Yay.
through a slightly different way, that's great. Are you okay with that? It's kind of a surprising formula, I think. It turns out that, like, yeah, your choice of x determines the volume, but in this weird way where it's a linear term minus a cubic term. I don't know, kind of weird.
Yeah.
Okay, time to optimize. You ready? Optimize.
Ready?
I'll change color, go red here. V prime would be, that's the derivative of volume with respect to x. So we get 12 minus, what's this going to turn into? 3/4 x squared, very good. And then we're going to set that equal to 0. Painting myself into a corner over here. But if you solve this and add that over, multiply both sides by 4/3, you end up with 16 equals x squared. Which means x has to be 4. So coming back here, go, oh, okay, I guess my x value. So now, yeah, what's the final answer? How do you express the actual answer to the question? It says, what are the dimensions that maximize the box's volume? Okay, well. By the way, this is kind of like we talked about yesterday. Could I, maybe, is it probably a good idea for showing my work purposes that I should maybe show a v prime number line and show that, yeah, obviously x can't be less than 0. But I can show that for any number between 0 and 4, say if I plug in 1, my v prime is positive, and for any number bigger than 4, my v prime is negative. That tells me that v goes up, down, like that. Yes. Okay. So that demonstrates that it's a max. But then again, like it's kind of, I would hope it's kind of common sensey that if we made this box enormously wide and like a millimeter tall, well, you could have 48 square inches of material and contain very little volume. Or you make it really skinny. X is 4. So what's the height if X is 4? 2? How'd you get the 2? Plugging into the constraint?
I also.
Very good. So if X is 4, so that's not so obvious. You gotta plug 4 in here, so you'd have 4 times 4 times h plus 4 squared has to equal 48, right? And so you get 16h equals 32. H has to be 2. Is that a tidy answer? That's pretty nice.
Mhm.
Pretty neato.
We're gonna have homework over break.
Yeah. 100 connect the dots puzzles.
Hell yeah.
3,000
Macedonia.
color by
Macedonian.
number
Oh.
sheets.
Oh god.
You'll each be handed a box of coloring books and a box of Crayola
I
crayons.
honestly would enjoy that.
Crayola, best brand crayons. Can we all agree on that?
I'm
You don't
sorry.
have Crayola.
I'm sorry.
What about crazy art though? I mean,
Come
come on.
Oh, this problem had a weird printing artifact on it. 21 is like lumped in.
Where are we looking?
I was just saying 21, there's like no room to do your work, but
How dare you?
luckily that problem's actually very fast. So.
Very
Dude.
Let's do we got some more time here. Let's pick one. Let's pick a fun one.
Wait, hold on. Are we
23.
gonna like take the quiz and then not have anything over break?
Yeah, we're gonna finish this before Friday, so no homework over the break.
Lit,
Oh, I-
lit.
JB.
What? I
Nobody
don't
likes
like
doing
homework.
math homework over
No,
Christmas break.
no.
Nobody likes doing
I
homework.
don't think homework should be a thing anyway, but especially on break. Okay, well, calculus, it makes sense.
I try to time things my best so that well, like if you're in physics, we're gonna be in the middle, but we're just gonna put it on pause.
Yeah.
Not gonna be any homework over the break. It's Christmas break, bro.
Lit.
Bruh.
The
What are we doing?
holiday season.
Let's do 19. Okay, it's a cylinder.
Well, nemesis.
My whole nemesis.
Oh, because this one we have the volume. We want to minimize the amount of material. And there's 3 circular surfaces. So it's a little bit different than your typical cylinder. We do have to kind of review. This is one you may not remember. It's your alarm.
Oh my God.
No.
Remember, you're a purple.
Okay,
Remember, you're a purple.
here's some food for thought for you. What is can you, through the sheer power of Thinky Winkies, remember what the surface area of a cylinder is?
Oh boy, it's
Two.
like.
They're like four.
Hold on, yeah, is it like, is it two?
Yes,
Oh, yes.
Jason's got it.
So
It's
wait a
two
minute,
circles.
what?
Well, just let's review the basics. A cylinder is, it's not like, so a cone is weird. A cone has a strange surface area formula that is very much not obvious. But a cylinder, if you think about it in the correct way, like Jason said, isn't a cylinder really just two circles and a rectangle? That's all a cylinder is two circles and a rectangle. So how big is each, what?
Nothing. You didn't hear my comments, so it won't be funny. But
Okay.
keep going.
How big is each circle? Well, assuming that the circles have a radius of r, here's the height. Well, the fuzzy wuzzy was a bear area of a circle is pi
Oh,
r squared, and there's two of them.
so it's 2 pi r squared.
Yeah. Good example of the banana theorem. Now this rectangle here, what's the length of that rectangle?
Circumference.
2 pi r,
Whoa.
and the height is h. So my total surface area of a typical cylinder, assuming it has a top and a bottom, would be 2 pi r times h plus 2 pi r squared. So in our problem here, slightly modified, this little cabinet has 3 flat shelves, so
So it's 3 pi r.
it's going to be 3 pi r squared instead of 2 pi r squared. So for 19, our constraint is that the volume, write this out. Constraint. The volume must be 24 pi. So roughly, whatever that is, like 75 or something. But we're going to keep the pi in there because, as you can see, there's pi's in the formula. The pi's are going to drop out. We're going to cancel this. What's the formula for the shelf that we're dealing with? The formula for volume.
Isn't that just height times?
2 pi r squared times like.
Yeah. So pi r squared, the base. So this is true for any solid that's has the same cross sections all the way up. Is just the base area, pi r squared, multiplied by the height. So that's true for any prism. Not true for a pyramid. For a pyramid or a cone, you'd have a factor of 1/3 there, if you're wondering. Cones, cone heads. You ever seen cone heads?
Yeah.
It's a pretty good little
The
map
best
right there. Huh?
The best chef.
It's good.
No.
It's a good movie.
No, I cared.
When he defeats that creature with the golf club, he hits the golf ball. It's these aliens that live like a American suburban life. He defeats this creature by he's been working at his golf game and he
Well, did you see like there was like an Israeli like rocket scientist who came out and said that aliens are doomed,
Oh,
but
yeah,
they're
yeah,
waiting
yeah.
for humans to be ready or something.
Wow.
Yeah, and that Trump is keeping the secret, which I thought was really, really, I don't know, it's just like what?
Would Trump be able to keep that?
Yeah, that's
He does have a
exactly
pretty
like.
big mouth.
Yeah, I was
Yeah.
like, that's it. I can't see Trump like learning about aliens and then being like, all right, I'm gonna keep it quiet from everyone. This doesn't seem
Yeah.
like the type of
That's
thing that
like
he
the
do.
truth.
We're gonna
Way to
minimize
see 'em on
the
there and,
surface area. Okay, minimize the surface area. So of course the goal for that would be, I need this device or whatever to contain this much material, this much volume, but I want to use as little material as possible to make it. So anyway, let's do that. So the surface area, so we're minimizing that quantity. So surface area is that, well, we have our modified formula, right? So 2 pi RH plus 3 pi r squared. There we go. All right. Okay, so we got to be clever with our substitution here. Should we solve for H or solve for R?
H.
I'm thinking solve for H, yeah. Because if we solve for
Yeah.
R,
Thinking.
we're going to have a square root involved. That's going to complicate things. So let's solve for H. So the pi's drop out, and you get H has to equal 24 over R squared. And we're going to sub that in. Sub.
Something that is elusive.
So our, what are we going to get here? Maybe we can do 2 steps at once if that's okay with you guys, because just to save space. So 2 times pi times, well, when you times by the 24, you're going to have 48, right?
Mhm.
So 48 pi, well, and then you're going to have, oh, the r squared will be on bottom. It'll cancel out one of the r's. There's certainly nothing wrong with having an intermediate step, right? I mean, if you want, if it helps you to replace the h with 24 over r squared, then yeah, you're good to go. So here, what's up? Question? So, does that make sense? Are we all okay with that? As you can see, if you're choosing R first, the bigger R gets, obviously the bigger this term gets, right? And the smaller this term gets. So anyway, let's do the derivative. Derivative. I was just pointing out that the graph, if you think about it, the graph would look something like this. So there's the asymptote at 0, and then this is the end behavior. So we know there's got to be some minimum. Does that make sense?
Yeah.
Okay. Derivative. Don't be afraid of pi, by the way. What is pi?
It's
just a number. 48 pi is a number, just like the number 6, right? So the derivative of 48 pi over r, you treat it exactly like you were doing the derivative of 6 over r or something. So what you're going to get is negative 48 pi over r squared plus 6 pi r. Get rid of my graph here. It's cluttering. Do we feel okay about that, guys?
Yes.
Yes, great. Okay, now I'm going to set this equal to 0 and do a little bit of arithmetic or algebra. So 6 pi r equals 48 pi over r squared. The pi's cancel out, of course, and you get, how many r's do you get over here? Yeah, your power is r cubed. And then divide by 6 on both sides, and you get 8. Oh my goodness.
Oh, there's no way. No.
An integer. Oh, amazing.
What?
2.
What?
Now, of course, if you go back to this constraint, this is why sometimes it's nice to put your whole constraint in a bubble, because then you can go back and, okay, I can just use this nice simplified version. 24 divided by 2 squared would be 6. So it turns out that kind of a skinny, not that skinny because it's the diameter is 4 and the height is 6, so 2 to 3 ratio. But
What?
Anyways, it turns out that the radius wants to be 2 and the height wants to be 6. Now, obviously, the numbers are not always going to come out to be integers. I picked 24 because 24 just happens to work out. That's an integer. If you made this 25, you would have an irrational solution. But okay,
Alright. Can I go to the bathroom?
Yeah, Jesse. We'll just end early today, guys.
Lit. 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 Lit.
Lit Savage.